Hello everyone, in today's video I'll be going over the problem Jump Game 6. So this problem gives you an integer array called nums and another integer called k. So essentially what you have to do is you have to start at the start and you have to move to the end, and every move you can do, you can move up to k steps. So, for example, since k equals 2, I can step 1 forward and go here, or step 2 forward and go here. And essentially, everything you land on, that number that number at the index of the array, that number will be added to a sum, and you want to maximize that sum. So yeah, so you can move at most k steps forward, and you have to reach the end, and then so when you reach the end here, you want to maximize the sum of your score, and um, your score is just simply all of the numbers you landed on added up. So in this situation, if you start since you start here, you can move forward to this, then move forward 1 2 to this, then 1 2, and that's the end, and that maximizes your score because you're adding up 1 4 3 and -1, and you're avoiding these two really negative numbers to decrease your score. So going into the solution of this problem, uh, because well, the first thing to notice is that the length of this is 10 to the 5, and k can also be 10 to the 5. So uh, we need to have at least like an n log n solution, right? So um, because we want to return the maximum score we can get starting from index 0, we can use dp by calculating what's the maximum score you can get starting from this index, then this index, and build it from the right to the left. Because it's really simple to see what is the maximum score you can get if you're already at the end, right? That's the equivalent of having an array with just one number in it, and since you start here and that's also where you end, your sum is whatever that number is, right? So in our array, we can fill in that this last number, whatever it is, we fill that in. So we fill that in here, and then we can figure out what is the best score you can get starting from the second to last spot. Well, um, we know that no matter what, we have to move forward till the last spot, because you want to reach the last index of the array. So then we can just check to see, we can just say if you start from here, well, you know you have to end here. So you can just take this and add it to this, and you can get the best one if you start from here, like the best score. And you can do a similar thing for this. So the third one, you know, since you're starting here, you have to add the value at nums, like the same index at nums, and you know you can move at most k steps forward. So well, we know what score we can get uh, if we take 1 step forward or 2 steps forward. Since we've already calculated this, this is what score we can get if we move 1 step forward, because this is the maximum score starting from here, and we also know the maximum score starting from here. So we can simply check to see which one is more, and then we can take this number at corresponding to this index and add it to the max of the rest of the array. And similarly for the next one, we want to calculate what is the best result starting from here. We can use a similar logic. So let's just say k equals 2. So we know we can step to here or here. And since we know, like, we already calculated what's the best score we can get starting from here and what's the best score we can get starting from here, we can take the maximum, and since we know we're starting from here, we also need to add this number at that index of nums. So in short, to calculate what's the best score you can get starting from any index. It's the the number at that index, obviously, because you landed on it. Since you're starting from it, you have to add that. And um, we know the maximum score for if we move forward from 1 to k times. So we want to take the maximum of whatever we already calculated. So um, I plus j, sure, where j goes from 1 to k, because this represents the best score we can get if we move forward to whatever spot we want to move forward to. And since we already calculated that this spot here or this spot here, the best score we can get starting from that, we don't need to like recalculate it, and we can just build it all the way until the start using this idea here, and at the end we can just return this start. But because k is at most 10 to the 5 as well, we can't just simply loop forward k times, because that'd be 10 to the 5 squared. That's like too slow. So what we can do is we can just maintain a priority queue which stores the best number that we have in our like next elements, right? So this priority queue will just store the maximum score that we can reach, like jumping from 1 to k squares. So yeah, that's about it for the solution. So let's get into how we implement this. So we first initialize our array, and this is just a simple check. Obviously, if there's only one element, we can just return that element. And we can make a class here, and this will just symbolize value symbolizes the score you can get starting at this index. So this will just help us keep track of what's the best score you can get starting from this index. So we will initialize a queue of this, and to compare two of these x's, since we want this to be in descending order, since it's a max priority queue, we want to have the best score at the front of the queue. We can just take b minus a, and this will reverse the order, because if it's a minus b, it will be the regular min heap. So then we can just initialize the end of this array to the last number, as we described earlier, and we can add that to our queue. So this will be a new instance of this class, and we initialize it with this is the value you can get starting from this index. So this is the index you start from, and this is the best score you can get. And then now we fill up our DP array. So we go to the next, like one from the end, and we go all the way until we can figure out what's the best score at the start. So we know we want to, at every square, at every index here, we know we want to find the best score that we can achieve within the next k indexes. So this simple check here is just while the best score is not in our range, like we can't jump there, we can just remove that. And so now after removing all the ones that we cannot jump to, so that'll remove like this, if let's say we can only jump 2 squares, then that'll remove all the stuff after 2 squares, and our priority queue will just be storing what's the max score we can get starting from here, and what's the max score we can get starting from here. And then we can simply look at the best score we can achieve, because yeah, and we can fill that out. So this here is essentially simulating this formula right here, because we know that this maximum value is the best value in all of the indexes we can jump to. That represents this, and we add this number to it because we're starting from it, so we need to add it. And we can simply add whatever we just calculated here, this number and this index. So that means In our queue, we'll have another like class, another object in the queue that represents like we just calculated the best score we can get starting from here. So now in our queue for this one, we can look and see if this was like the best score calculated so far. We can look and refer to that. And after filling out the entire array, we can just simply return the first one. Since our DP array represents the best score we can get starting at that index, returning this will be equivalent to the maximum score you can get starting at index 0. So if we submit this, it should work, and the runtime of this should be O of n log n, because this for loop will iterate n times, and pulling and adding are both log n operations. So we know it will work because like n and k are at most 10 to the 5. So yeah, that's about it for Jump Game 6. Thank you for watching, and I hope you enjoyed the video.